What could be calculated on a slide rule depended on what scales the slide rule had. Some slide rules had a large number of scales. This slide rule could calculate many things. My simpler slide rule down here only has a few scales. It can calculate only a few things. However, the earliest slide rules had many different kinds of scales. James Watt of steam engine fame had a special slide rule developed for his engineering firm. Peter Roget was the first to come up with log-log scales, that's logarithms of a logarithm, and they're handy for calculating the power or roots of any number. And he did that before he published his famous thesaurus. Even though slide rules were known in the 17th century, it wasn't until the mid-1800s that they became popular. And they became popular because a scientist by the name of Amédée Mannheim standardized the slide rule and invented something that was new, and that was the cursor that could be slid along over the scales like this. A Mannheim slide rule can calculate any number between 1 and 10. It can multiply or divide. But in physics, we often have lots of numbers much larger or much smaller than 1 or larger than 10. But we can use scientific figures, scientific notation, to turn any number into a number between 1 and 10. 300 can be written as 3.0 times 10 to the second. 25 can be written as 2.5 times 10 to the first. So let's see how we might calculate something on a slide rule. Let's start easy. 2 times 3. We would move our cursor to the 2 on the D scale down here. Then we would move the 1 on the C scale, which we call the index, directly above it. Then we would move the cursor to the 3 on the C scale, and the answer is directly below it, 6. If we wanted to multiply 300 times 25, we would put the cursor on 3 times 10 to the second, and the index directly above it. And then we would move our cursor to the 2.5, and our answer is directly below it, 7.5. So 300 times 25 is 7.5. Add the exponents times 10 to the third, or 7,500. Now, let's try another number that may be a little more difficult. What about 5 times 6? Well, we do it basically exactly the same way. We set our cursor on the 5 on the D scale. We put the index on the C scale directly above it, and then we move our cursor to the 6. But there's not a scale out here, but that's okay, because we can move our slide because either end of the scale is called the index, so we will put our index on the other side over the 5. Now we can move our cursor to 6, and here's our answer, 3. Oh, now we still got to worry about that decimal point. Most of us know that 5 times 6 is not going to be 3, it's going to have to be 30. We have to keep track of that decimal point. That even made it into literature. In Half Spacesuit Will Travel by Robert Heinlein, the hero, Kip, said, On a slide rule, such a problem takes about 40 seconds. Most of it to get your decimal point correct. Now, what about division? Well, division is actually easier than multiplication. If we think we want to divide, say, 6 divided by 2, we know that we can change that to a fraction, 6 over 2. To use a slide rule, you simply invert it. So we will find 6 on the D scale. We will put 2 directly above it, and the answer is going to be under the index, 3. So we can multiply and divide using a Mannheim slide rule. We can also do a couple of other things. We can do squares and square roots. For example, if we want 3 squared, we can put the cursor on 3 and look up here on the A and B scales and see that it's 9. If we're interested in the square of 6, we put our cursor over the 6, look up here, and we see that it's 3.6. Oh, 6 squared is going to be more than 3.6. It must be 36. This scale is going to be used for our odd number of powers of 10. And this scale right here would be used for our even numbers of powers of 10. And so if we want to find the power of 25, the square root of 25, that would be 2.5 times 10 to the first. So we would have to use this scale right here. We'll put this on 2.5, and the answer is down here at 5. If we want the square root of 256, that would be 2.56 times 10 to the second. So that means we're going to have to use this side. 2.56, here's 2.5, and about 2.56. And our answer is going to be down here. It's going to be 1.6. Oh, it's going to be 16. We have to keep track of those decimal points.